Let's create the load. We'll call it concentrated forces at corners, activate it in the apply force step, and set it to type concentrated force. Abaqus prompts you to select the points for the load. Select the two corner points at the bottom of the free end of the beam in the viewport. Give the concentrated forces a magnitude of 4 million newtons in the negative y direction. Note that this force is applied at each node, so since we have two nodes, that gives us 8 million newtons. We need to identify and name the surfaces that will come in contact so that we can specify the contact interactions. Let's create some surfaces. Expand the assembly container in the model tree and double-click Surfaces. Name the surface Rect Block Bottom. It is hard to select the bottom of the rectangular block in the viewport since the plank is underneath it. One way to make it visible is to temporarily suppress the face-to-face constraint between the rectangular block and the plank. In the assembly container in the model tree, expand Position Constraints. Right-click on the appropriate face-to-face constraint and choose Suppress. You can now create the surface as you can select it in the viewport. Now resume the surface-to-surface constraint. Create another surface called Curve Block Top using the top surface of the curve block. Create a third surface called Plank Bottom using the bottom surface of the plank. And create a fourth surface called Plank Top using the top surface of the plank. Now let's define the contact interaction properties. Double-click Interaction Properties in the model tree. In the Create Interaction Property window, name the interaction property Frictionless and set it to type Contact. In the Edit Contact Property window, click Tangential Behavior in the Mechanical menu. Set the friction formulation to Frictionless. Click OK to close the window. Let's define another contact interaction property. Name it Frictional and set it to type Contact. In the Edit Contact Property window, click Tangential Behavior in the Mechanical menu. Abaqus uses the Coulomb friction model for frictional interactions. Ideal friction behavior requires for two surfaces sticking together to remain that way till the shear stress exceeds the critical shear stress, and when that happens, they suddenly start slipping. However, this ideal behavior is difficult to simulate, and Abaqus provides a few other options. It is usually advisable to use a penalty friction formulation. This formulation allows a small elastic slip even when the two surfaces should be sticking. Abaqus will automatically choose the penalty stiffness such that this allowable elastic slip is a very small fraction of the characteristic element length. The static kinetic exponential decay allows the user to specify static and kinetic friction coefficients. In this friction model, the static friction coefficient decays exponentially to the kinetic value. Test data can also be entered to fit the exponential model. In addition, you have the option to specify elastic slip. If you wish to enforce ideal frictional behavior, go with Lagrange multiplier. With this formulation, there will be no slip between the surfaces till the shear stress has crossed the critical shear stress. The rough formulation specifies an infinite coefficient of friction, meaning that there is no slipping between the surfaces no matter how high the shear stress. And user-defined allows you to specify the shear interaction with user subroutines. Set the friction formulation to penalty. You see three tabs: friction, shear stress, and elastic slip. Let's focus on the friction tab. Leave the directionality set to the default of isotropic. This tells Abaqus that a uniform friction coefficient should be applied in all directions. Anisotropic allows for different friction coefficients in the two orthogonal directions on the contact surface. The options for slip rate, contact pressure, and temperature-dependent data do as their names describe. They allow you to tell Abaqus whether or not the friction coefficient is dependent on slip rate, contact pressure, or temperature. We will leave these options unchecked. In the table, we shall set the friction coefficient to 0.1. Let's turn our attention to the shear stress tab. You have two options for the shear stress limit: no limit and specify. No limit tells Abaqus that the shear stress does not need to exceed some critical value for the surfaces to slide. With the specify option, on the other hand, you tell Abaqus the shear stress limit. When the magnitude of the equivalent shear stresses reaches this value, sliding will occur regardless of the magnitude of the contact pressure stress. We shall leave the shear stress limit set to no limit. Now let's consider the elastic slip tab. Since we are using Abaqus Standard, we can specify the maximum elastic slip. Fraction of characteristic surface dimension allows the user to specify the maximum allowable elastic slip as a fraction of the characteristic contact surface length. Absolute distance allows the user to enter the absolute magnitude of the allowable elastic slip. We shall leave fraction of characteristic surface dimension set to Abaqus's recommended value of 0.005. Click OK to close the window. We now have two interaction properties, frictionless and frictional. Now that we have created surfaces and interaction properties, we can proceed with creating the interactions. Double-click Interactions in the model tree. Name the interaction Curved Plank Interaction, as it will define contact between the curved block and the plank. Click Continue. Abaqus prompts you to select the master surface. You can select the surface in the viewport, but we've already created surfaces, so click on the Surfaces button. In the Region Selection dialog box, select Curved Block Top, and check Highlight Selections in Viewport to see the section highlighted. Click Continue. Abaqus then asks you to choose the slave type. Choose Surface. Once again, you see the Region Selection dialog. Choose Plank Bottom and click Continue. You see the Edit Interaction window. Here, Abaqus tells you which surfaces you chose as master and slave and gives you the option to switch them. Let's talk about why we chose these options. There are two types of contact discretizations in Abaqus: node to surface and surface to surface. In node to surface, the nodes on one surface, the slave, contact the discretized segments on the other surface, the master. It is not possible for the nodes of the slave to penetrate the discretized segments on the master, although the nodes on the master may penetrate into the slave surface. For this reason, the choice of master and slave is important. The surface you select as slave should be the more finely meshed surface, and if the mesh densities are similar, the slave surface should be the one with the softer material. The surface-to-surface contact formulation, on the other hand, considers the shape of both the master and slave surfaces in the region of contact, and enforces the contact conditions in an average sense over regions near the slave nodes rather than on individual slave nodes alone. Large penetrations of master nodes into the slave surface do not occur with this discretization. Hence, the choice of master and slave is not as important, but the same surface selection guidelines as node-to-surface discretization should be followed where possible. Since node-to-surface discretization simply resists penetration of slave nodes into the master surface, forces tend to concentrate at these slave nodes, which leads to spikes and valleys in the distribution of pressure along the surfaces. Since surface-to-surface discretization resists penetrations in an average sense over regions of the slave surface, this has a smoothing effect. Generally, surface-to-surface discretization provides more accurate stress and pressure results. However, it also involves more nodes per constraint and can therefore be more computationally expensive, although in most applications this extra cost is fairly small. Although surface-to-surface provides more accurate stresses than node-to-surface, as the mesh is refined, this discrepancy becomes less. Abaqus Standard offers two tracking approaches that account for the relative motion between two interfacing surfaces: finite sliding tracking and small sliding tracking. Finite sliding allows for arbitrary relative separation, sliding, and rotation of the contact surfaces. The connectivities of the currently active contact constraints get updated based on relative tangential motion of the contact surfaces. Small sliding, on the other hand, assumes there will not be much relative sliding between the surfaces. The connectivity constraints between the nodes involved remain fixed throughout the analysis, although the active-inactive status of the constraints can change. Small sliding tracking is based on linearized approximations of the master surface per constraint and is computationally less expensive. However, your assumption of small relative sliding between the surfaces must be valid, or you will get incorrect results. You see four tabs: Slave Adjustment, Surface Smoothing, Clearance, and Bonding. We will not be changing these options in this example, but I would like to familiarize you with them. Slave Adjustment adjusts the position of the slave surface of a contact pair. Slave Adjustment is useful in eliminating gaps or penetrations caused by numerical roundoff from graphical preprocessors such as Abaqus CAE. These might cause convergence issues during the analysis, and slave adjustment can be used to move the slave surface in order to minimize or get rid of the gap or penetration between the surfaces. The adjustment made by Abaqus will be strain-free. It is recommended to adjust contact surface pairs when using small sliding contact. Mesh discretization, especially a coarse mesh, causes inaccuracies during the contact calculations. When automatic surface smoothing is selected, Abaqus can identify axisymmetric or spherical surfaces in the contact pair and smooth them. Clearance allows you to specify an initial clearance between nodes on the slave and master surfaces when using the small sliding formulation. For initially bonded contact conditions, bonding allows you to restrict cohesive behavior to a subset of slave nodes. For the contact interaction property, choose frictionless, which we'd created earlier. Click OK. Create a second interaction called rectangular plank interaction, as it will define contact between the rectangular block and the plank. Set rect block bottom as the master surface, and plank top as the slave surface. This time set the contact interaction property to frictional. All that's left to do now is mesh the parts and run the simulation. Mesh all three parts using 8-node linear brick reduced integration elements and an approximate global size of 4. create a job called contact simulation job and run it. Let's view the results to make sure everything ran correctly. Plot the deformed shape in the viewport. You see the expected behavior. The plank successfully contacts the curved block and bends along it. The rectangular block, on the other hand, holds the other end of the plank in a horizontal position just as it should. Let's look closely at the contact pressures. Plot a color contour on the parts. By default, the MESA stresses are displayed. Change the primary variable to contact pressures, or CPress. You can see color contours on the plank and the curve block. The presence of contact pressures indicate that contact has occurred. Since we made a special step, make contact, just to establish contact, let's make sure that contact did actually occur in that step. Bring up the Frame Selector tool. Move the slider to observe when contact pressures appear on the plank and curve block. It would appear that contact pressure is present on the plank in both the Make Contact step and the Apply Force step as expected. However, there does not appear to be contact between the plank and the curve block in the Make Contact step. It is possible that the contact pressures are much higher between the rectangular block and the plank than between the plank and the curve block, and the range of the color contour is too large to indicate subtle differences. So let's remove the rectangular block and the plank from the display. Use the Replace Selected tool from the Display Group toolbar. In the prompt below the viewport, choose Part Instances as the entities to replace. Click on the curve block to select it, and then click Done. The curve block replaces everything else in the viewport and is the only part displayed. Now we move the Frame Selector slider again. In the last increment of the Make Contact step, you see contact pressure is displayed on the curve block. This confirms that contact was established in the Make Contact step, even though these contact pressures are a lot less than that between the rectangular block and the plank. Use Replace All from the Display Group toolbar to replace the current view with all of the parts. This concludes the contact tutorial. Contact is a complicated subject, and as you can see, there are many options you can play around with. Convergence issues are frequently encountered when contact interactions occur. The Abaqus documentation is your friend when dealing with the subject.